We are Team 2206, Autonomous Search and Rescue Helicopter System Design. Our sponsor is Sikorsky Aircraft. Our academic advisor is Ashwin Dani. I am Nathaniel Metke.
I'm Kevin.
I'm Yuri Lei.
I'm Terry Joe.
The goal of our project is to complete a search and rescue mission using our autonomous drone. We will split this into two main objectives. The search component will involve scanning an area with a 30-foot radius in order to find all potential targets and to create a flight path for the drone to correctly identify the rescue target. The rescue part of the project will involve a controlled approach, target validation, and rescuing the target to safety.
Our off-board computer handles the majority of the computation during the flight to determine where the target is located as we navigate through our survey mission. We use the standard computer vision library OpenCV as well as blob and edge detection algorithms to locate our target within the image. We record when and where we saw them so we can navigate back to pick them up. The other sensor connected to the Raspberry Pi is our time of flight distance sensor. It is used as we are approaching the target to determine when we are less than 1 yard away from the ground when we transition to prepare for target pickup. Here, we can see a demonstration of our computer vision targeting in action, tracking a person moving around the room from different distances.
We organized the flight operation into a series of state transitions that can be modeled by two state machines. These state machines are mirrored on the Raspberry Pi and Simulink Flight Director. As mentioned earlier, we divided the overall flight state machine into initialization, which involves arming the drone and sending the survey mission waypoints, takeoff, where the drone ascends to a predetermined altitude, survey, where the drone takes the survey mission path created during initialization and captures images of the area, mission, in which the drone approaches the target waypoint detected and defined by the camera and path planning algorithm, controlled approach, and return to launch, where the drone reascends and flies back to its launch point. Because controlled approach is a multi-step process, we have a substate machine specifically for this phase, which includes descend, hover, drop, and verify. On the right are the C++ enumerations created to model the state machines on the Raspberry Pi. There is a back and forth communication of custom messages between the Raspberry Pi and Simulink Flight Director to ensure the two state machines are synchronized throughout the drone flight's entirety. Navlink communication on the Raspberry Pi is done using an API called Nav SDK to send and receive messages at a high level of abstraction. Implementing custom messaging on Simulink involves sending and receiving messages through utilization of a combination of Simulink blocks and MATLAB functions.
In this project, we will task to design a flight director in Simulink to approach and rescue our target using a winch system. Our flight director will be designed using components in the UVA PX4 supporting package in Simulink. We also implemented the state flow in our design to easier monitor the state in our flight plan. This includes takeoff, survey, mission, control approach, and return to launch.
For the drone hardware, we have the X500 ready-to-fly drone from Holybro. As you can see, we have the GPS module, the Pixhawk 4 flight controller. Underneath, we have the power netting board for the motors, and the battery and the servo motor with the brackets underneath. Over here, we have the Raspberry Pi connected to an infrared camera. These will be added later to our drone.
Here is a high-level block diagram of the drone system. The IR camera and an ultrasonic sensor are connected to the Raspberry Pi, and the servo motor, accelerometer, gyroscope, and GPS are connected to the Pixhawk 4. To summarize the entirety of the flight process, essentially target waypoints are created from the image input to the Raspberry Pi, which are then sent to the flight director, where travel to the waypoint and controlled approach to the target are guided by the drone plan. The interaction between the Pi and flight director is determined by the current state of the drone regarding the overall and controlled approach state machines.
The rescue component of our project will begin once the drone is hovering over the rescue target. It will deploy a winch using a neodymium magnet in order to rescue the target. OpenCV will be used to validate a successful pickup, and if needed, the winch will be redeployed. This is a video of our servo motor in action. As you can see, it can deploy a magnet and retract it in order to pick up our target. It will be able to handle 1 pound of weight, which is sufficient for our project.